Hello, in this video I'm going to be talking about hybridization. I'm going to be giving an introduction, then I'm going to be going over the relationship between hybridization and electron geometry, then I'm going to go over some practice problems, and finally I will give you some practice to check your progress on this topic. If you're new here, my name is Liah, and on my channel you can find science and math videos. Let's start with sp3 hybridization. Now sp3 are orbitals, 4 of them to be precise, each one made up of 1 part S and 3 parts P, right? And this hybridization, right, these S and P orbitals are mixing, well, that's going to produce an orbital that is a mix of the S and P orbitals. Now here we have the orbital diagram for carbon's valence electrons, right? They're both in the level 2. And what we're going to do for this sp is that this s orbital is going to be elevated, all right, and these p orbitals are going to be lowered in energy, all right, so that we can make these sp3 orbitals, okay, a mix between the energies from the s orbital and the energy from the p orbitals. And 1 electron is going to go into each orbital. Now, because these are half-filled, we can see that there are 4 places for an electron to go into, meaning that there are 4 possible bonds that this sp3 carbon can make. Let's use CH4, also called methane, for our sp3 example. So this is a 3D drawing of methane. Okay, you have your center carbon and 4 hydrogen atoms surrounding it. Now, right here, we have carbon with its sp3 hybridized orbitals. Okay, notice that these orbitals are not exactly spheres, like an s orbital would be, and not exactly these 2 lobes that a p orbital would be. They're rounder than a p orbital, and they're a little longer than a s orbital. Okay, they're a hybrid, they're a mix of this combination. Alright, so knowing that these in yellow are the sp3 orbitals of carbon, we have these 4 hydrogens that we need to attach. The thing to know here is that when hydrogen comes in bonds, hydrogen's orbital is spherical, okay? It's an s orbital, and it's going to overlap, okay? And so this is the overlap between an s orbital right here and the sp3 orbital in yellow. Now let us add 3 more hydrogens to this. So again, we have this s orbital overlapping, okay, for another attachment of hydrogen, and then we have another bond here and another bond here. So what we observe in this diagram here is that the 4 hydrogen atoms are going to come with their s orbitals, and those s orbitals are going to overlap the sp3 orbitals of carbon. That is what is happening over here in this simplified drawing with just bonds. In each bond, there is an overlap of orbitals. So when carbon makes 4 bonds, the hybridization of that carbon atom is called sp3. Let's move on to sp2. Now again, I'm going to really quickly draw carbon's valence orbital diagram. Okay, so we have the s and the p orbitals. Now, for sp2, as you notice, we still have 1 part s, but now we only have 2 parts p. So what we're going to do is we're going to have a total of 3 hybridized orbitals. Okay, let's move them in between the energy of these 2. All right, and we're going to call these 3 orbitals sp2. Notice, now we have used 2 p orbitals and 1 s orbital. And we have a p orbital left over because this was not included in the hybridization. All right, so keep in mind that this p orbital is left over. All right, now just go ahead and fill in our electrons. Okay, and in this p orbital, it's going to be 1 electron. Okay, because remember there was 4 valence electrons for that carbon. Okay, so in sp2, we have 3 hybridized orbitals that are called sp2 and 1 p orbital left over. Now for this, we're going to use the molecule C2H4, which looks like this in Lewis structure. As you can see, it is 2 carbon atoms bonded by a double bond, and then each carbon has 2 hydrogens. Now let's draw the hybridization diagram for this. So carbon is going to have 3 hybridized orbitals, okay? And the same goes for this carbon over here, 3 hybridized orbitals. Now between these two, these sp2 orbitals will overlap, creating this sigma bond. Alright, now let's bond the hydrogens next. So hydrogen, as we saw in the last example, comes with its s orbitals and overlaps now with the sp2 orbitals of carbon. Okay. Alright, now we have our hydrogens drawn. Now, where's this double bond coming from? Where's the overlap for that? Here it's just a single bond. Let's not forget this p orbital. Each carbon has one. So there's going to be a p orbital here and a p orbital over here for this carbon. And what's going to happen is that the p orbitals from this carbon and this carbon, so the one on the left and right, these are going to overlap. And of course the electrons are in here, okay? The electron from hydrogen and from the sp2 orbital, I'm just not drawing them here. Okay, but they're there. As we know that they are in these bonds, there's 2 electrons there. Okay, but back to this p orbital, this overlap is going to be here, creating the pi bond. So in yellow here, we have the sigma bond, denoted by this Greek letter, sigma, and we have sigma bonds between carbon and hydrogen. Okay. And we have a pi bond denoted by the white overlap of p orbitals. A question that you might be asking yourself is, well, if there are p orbitals, why are these 4 lobes here? All you have to remember is that a p orbital looks like this. So this is 1 p orbital. All right, therefore, for 1 p orbital, we have this on 1 carbon. They're just separated by that atom in the drawing. And so as you see, a combination of 1 pi bond and 1 sigma bond will equal a double bond, and the overlap from an sp2 orbital and an s orbital creates single bonds. Okay? And as you can see, an sp2 carbon is bonded to 3 things, 3 atoms. Finally, let's look at sp. And for this, we're going to use the molecule C2H2, and this is its Lewis structure. Once again, we are using carbon's valence electrons, so I will draw them real quickly here. Now, for sp, we have 1 part s and 1 part p, and both of these are going to be called sp orbitals. Okay, they're hybridized. They're a mix of the s and p like we saw earlier. Now, if we're using 1 s orbital and 1 p orbital, we have 2 p orbitals left. So let's make a note of that for ourselves. These are going to be p orbitals over here. Alright, so now let's draw the hybridization diagram for this molecule here. Each carbon atom will have 2 sp orbitals. The ones in the center will overlap as a sigma bond, and then we will have the hydrogens. As usual, the hydrogens will come with their s orbital and overlap with the sp orbital. Now, in this drawing, we see that the sp orbital, in yellow here, is overlapped with the s orbital of the hydrogen, same here. And in the center, we have 2 sp orbitals overlapping each other, creating a sigma bond between these 2 carbon atoms. Now we need to make sure that we're drawing triple bond in this hybridization diagram. And so we have to remember that each carbon has 2 p orbitals. Okay, so we'll draw one like this. Alright, so here's one p orbital for each carbon. Now we're going to draw another p orbital for each carbon. Alright, and so we will show this in white. Okay, there we go. And so, like in the other one, we're going to overlap p orbitals. So the green p orbitals are going to overlap, and the white p orbitals are going to overlap. Now, if it's not clear from this drawing, the p orbitals are perpendicular to one another. So you have the green ones going up and down, okay, like this, and you have the white ones going at an angle to that, specifically 90 degrees, okay, because that's perpendicular. And so we can go ahead and label these. We can go ahead and label that the S and the sp overlap between carbon and hydrogen is sigma bond. And then we have the sigma bond between the two carbons in yellow. And we have pi bonds in white and green. And so a triple bond is made up of 1 sigma bond and 2 pi bonds. Now very quickly, I'd like to run through the relationship between hybridization and electron geometry, and as a little bonus, I added bond angle as well. If hybridization is sp, our electron geometry is called linear, and as this linear implies, our bond angle will be 180 degrees. For sp2 hybridization, we have electron geometry called trigonoplanar, and our bond angle would be 120 degrees. Finally, for a hybridization of sp3, the electron geometry will be called tetrahedral, and the bond angle will be 109.5 degrees. So it might help when you're doing your homework or your exam that you can find hybridization by looking at the electron geometry. Let's do some practice problems now. And what we're going to do is find the hybridization of non-hydrogen atoms, so of the atoms that are not hydrogen. Okay, because hydrogens always are going to make one bond, they're never going to have any lone pairs around them, and so we don't really need to worry about finding their hybridization. Alright, so let's start with this one, BH3. The hydrogens are 120 degrees apart from one another, and we also know that the electron geometry of this is trigonoplanar. Therefore, we can conclude that the hybridization is called sp2. Let's go to the one in green. The oxygens look the same, meaning that they both have a double bond and both have 2 lone pairs. So we can determine the hybridization from the electron geometry, or we can go ahead and just count the groups. The groups meaning 1 lone pair equals 1 group, and a connection to an atom is 1 group, whether it's single bond or triple bond or double bond. Okay, 1 atom is just 1 group. So we can see for this oxygen right here that it has 2 lone pairs, plus it's bonded to 1 other atom. And so 3 groups equals sp2, and an electron geometry of trigonoplanar. So both of these oxygens are sp2 hybridized. Now let's do the hybridization of this center atom. So the center atom has 1 group and 2 atoms, so that's 3 groups, and so the sulfur will also be sp2. Alright, now moving on to this N2, we see that we have nitrogens that look the same. Both are bonded to 1 lone pair and a triple bond. So here we can see that there's 1 group in the lone pair and another group in the 1 atom that it's bonded to. And so each of these nitrogens has a sp hybridization. Its electron geometry is linear. Finally, let's find the hybridization of the oxygen in water, H2O. So water here has 1, 2 groups plus 3, 4 from its atoms. So something that's bonded to 4 groups is called sp3 for its hybridization. It's a tetrahedral geometry. If you're in general chemistry, you probably won't have to worry about this, so you can just go to the timeline and skip to the check my progress part. So let's find the hybridization of the non-hydrogen atoms. Right, so I will assume that you know how to read bond line formulas. Okay, so at this end we have the carbon here attached to 3 other hydrogens and 1 carbon atom, meaning that it has 4 bonds, making it sp3 hybridized. So let's find the hybridization of this carbon right here. So let's find the number of groups it's attached to. So one group from this carbon right here, another group from this carbon right here, and a final group from the implied hydrogen, making it sp2 hybridized. Now let's do this carbon right here. So this is again sp3 because it's at the end. So let's find the hybridization of this carbon now in the center here. So this carbon is bonded to a carbon here, and a carbon here. 3 groups. That makes this carbon right here sp2 hybridized. Now let's do the hybridization of this carbon right here. This carbon is attached to this carbon right here, and 2 hydrogens that are implied. And so that carbon right here is going to be sp3 hybridized. Now moving on to this carbon right here. This carbon is attached to a carbon right here and a carbon right here. Now that's 2 groups, and a carbon attached to 2 groups is called sp hybridized. Lastly, we will do this carbon right here. So this carbon is attached to 1 hydrogen and 1 carbon right here. That's 2 groups. And so therefore this carbon is sp hybridized as well. Let's do this molecule right here. Alright, so a carbon at the end we know is sp3 hybridized. Now let's do the carbon right here. So this carbon makes a bond to this carbon over here, this carbon over here, this nitrogen over here, and 1 implied hydrogen. Now that is going to be 4 groups in total, therefore this carbon right here is sp3 hybridized. Now let's do the hybridization of this nitrogen. So this nitrogen has 2 groups, plus 1 group, plus another group. So in total that's 4 groups. So this nitrogen is sp3 hybridized. Now let's do this carbon right here. So this carbon is bonded to this carbon, and then it's bonded to this carbon over here, and it's bonded to 1 implied hydrogen right here for a formal charge of +1. And so this carbon right here is sp2 hybridized. Next we have a carbon at the end, and we know that carbons at the end are sp3 hybridized when they are bonded by a single bond to the rest of the molecule. Okay, so now we will go on with this molecule right here. Okay, so let's find the hybridization of this carbon right here. So this carbon right here, well, it has a negative formal charge. Now, what does that mean? Well, it means that it's bonded to 2 hydrogens, and it also has 1 lone pair, okay, making its formal charge of -1. I made a formal charge video, so you can check that out if you want to see how we got this. Alright, so it has 1, 2 atoms, 3 atoms, so that's 3 groups, and then lone pair, so that's 4 groups. Remember, the groups are atoms or lone pairs. So 4 groups is sp3. Now let's do the carbon right here. So we already know from above that a carbon attached to a double bond, a single bond, and an implied hydrogen has an sp2 hybridization because it's bonded to 3 groups. Same goes here. Okay, double bond, single bond, and an implied hydrogen. And then over here, we have bond here, and then 2 implied hydrogens. So that's 4 groups. So this carbon right here is sp3 hybridized. And finally, this chlorine. Well, this chlorine has 1 group, 2 group, 3 group, and 4 group right here. So it has a bond to a carbon atom and 3 lone pairs. And so that is sp3 hybridized. Now here we have a benzene ring. And we're going to find the hybridization for each carbon. But we'll only need to find hybridization for 1 carbon because all the carbons here are identical. Each has a double bond, and each has 1 implied hydrogen. Now, looking right here, we can see that this carbon makes a bond here, and a bond here. So that's 3 groups. Now, something with 3 groups is called sp2 for its hybridization. Alright, so all these carbons are sp2 hybridized. Finally, let's do the hybridization for each carbon atom here. Again, we'll only need to find the hybridization of one of the carbons because all of them are identical. Okay, each has 2 hydrogens, okay, and then 2 bonds to 2 other carbons. So for example, this carbon right here. This carbon right here is bonded to this carbon, and 2 hydrogens. So that's 4 groups. And therefore, each of these carbons in the corners of this cyclobutane are sp3 hybridized. Now it's time to check your progress with this topic. So find the hybridization for all non-hydrogen atoms in each molecule, and then double check by using the electron geometry. So here are the 3 molecules that you can practice with. Thank you so much for watching. If you want to see more videos of these in the future, make sure that you subscribe and click the little bell so that you know immediately when I post a new video. I'll see you next time.